Good afternoon, everyone. Hello, my name is Roger Hedding, and welcome to today's webinar. The normal facilitator, Carrie, for this is on vacation, so I'm going to handle the duties of the presenter and also the facilitator. If you have any questions throughout today's presentation, please type them into the question box on the GoToWebinar control panel located on the right-hand side of your computer screen down here. I'll try to get to as many of those questions as possible after I finish the presentation. Let's see. This webinar is brought to you by the Railline Product Advanced Protection and Control IEDs from ABB. This is the disclaimer we have to read. ABB is pleased to provide you with technical information regarding the protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in the ABB Web-Based Protective Relay School, you agree that the ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any actions taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations based on improving safety, efficiency, and profitability. Contact the ABB sales representative for any further information. The subject of today's first of a series of Protective Relay School courses is Introduction to the Protection and Control. Again, it's presented by me, Roger Hedding. I won't go into the gory details about my biography, but I've been with the ABB now for 45 years, starting with Westinghouse back in the early days, and you can read for this. Right now, I'm a senior consultant for ABB, and I'm a senior life member of the IEEE and past chair of the IEEE Power Systems Relaying Committee. You can read the rest yourself. Not a very flattering picture, though, is it? Today, what we plan on doing today is we'll have an overview and understanding of the role of relays in protection and control. This is what we plan to get, points we plan to get across. We'll define relay classifications, review common relay applications, give you a bit of understanding in the relaying philosophy, review basic protection principles, review the IEEE device function numbers, because the relay world has a shorthand, a way of describing different pieces of protection, and the shorthand are these relay device numbers. We'll talk a bit about them. And then we'll talk a little bit about the IEEE and IEC symbols, because they're somewhat confusing with respect to each other. Again, if you have any questions, just put them in that question box, and I'll get to them after the presentation is over with, hopefully. Let's start with the basics. What is relaying? If you look at the dictionary, it's defined as an act of passing something along from one person, group, or station to another, or a supply as of horses arranged beforehand for successive relief, or a number of persons who relieve others in some work, or an electrically operated switch that responds to current or voltage in one circuit to switch on and off the current in the second circuit. Where does this word relay come from, you may ask? The word relay was derived, at least one derivation, derived from the French word relays, which at that time meant replacement. The term relay was first applied in 1830 to a team of fresh relief horses that pulled horse vans, railway cars, on wooden wheels on a wooden railway between Baltimore and the Ellicott Mills. That's a picture in what's shown in this picture. The term relay also was applied to the station where workhorses were changed for fresh horses to continue the journey without delay. Of course, in the Old West, stagecoaches had relay stations. And in 1860 and 1861, the Pony Express moved mail across the West in relays from one person to the next. About that same time, electromagnetic technology was starting to evolve. Back in 1830, Joseph Henry designed the telegraph electromagnet, where he noticed by closing a contact on a circuit, he could transfer that contact information along a circuit to another load some distance away. The remote electromagnetic device with close contact in series with the battery and the load that you see in the far right-hand side here. Then Samuel Morse took this one step further and to go much greater distances with using sounders, repeaters, and developed this Morse code that people use for transmitting information across the country, using the key at one end and then various sounders and then repeaters at the other end, so they would be able to decode what the person was keying in at the far end of the line. There was some similarity between the sounders and repeaters and the relay horses that were used in the transferring the information or transferring people across the country, and that so they started to call these repeaters and sounders relays. Hence the derivation of the word relay in our vocabulary now. So I just said, recognize the similarity of function between the relay of the horses and the telegraph repeaters and sounders. Telegraph electromagnetic devices became called relays by the 1870s. These first electric relays were used in long-distance telegraph circuits, repeating the signal coming from one circuit and retransmitting it to the other circuit. If you look at the early 1880s electric power system, it was very, very, the system wasn't evolved at all. And when a fault would happen on the system, the only thing that would be interrupting would be the lighting circuit, so it wasn't very important at all. So they intentionally had the weak links, which were thinner wires that would be the things that would burn down from an overload. Later on, these weak links were replaced by fuses, and which weren't maintained very well, as you can see from the quote from B.H. Todd, that the improper replacement of fuses is one of the deepest rooted evils in the electric industry, where people would replace fuses with something larger so that the circuit wouldn't, the fuse wouldn't blow and they would be able to continue their service. Finally, these fuses were replaced by electromagnetic operating switches, but still didn't have any fault discrimination. And later on, we applied this relay technology. If you look at the evolution of relay technology, back from the very first relays in the late 1800s, early 1900s, which is the meter type of enclosure, we've gone through a huge evolution, starting with the electromechanical relay. That's been evolved and evolved, as you can see several iterations of that. And actually, the electromechanical relays are still used on quite a few of your systems, and they're still being manufactured in one of our plants in Coral Springs, Florida. The electromechanical relay had some problems because of vibration. Stuff could cause them to operate, or they needed a lot of maintenance to be done, but they would last for over 50 or 60 years, as you know by what's happening in your systems. When solid-state devices started becoming popular, the transistor and whatnot was developed, then they started to investigate replacing the one-for-one type of electromechanical relay with a solid-state relay. And these found their ways into lots of nuclear power plants because solid-state relays didn't have the vibration characteristics that a electromechanical relay had, so that wouldn't so when it would be able to withstand the seismic vibration without operating. The solid-state relays then gave way to the numerical relays and microprocessor relays that you see. And then we've gone through several iterations and generations of microprocessor relays back from the mid-1980s to the present, or the last 30 or so years. People ask still, I remember when I gave the first couple of presentations on microprocessor relays back in the late 80s, people would ask, how long would these relays last? How long could we surely can't get 50 years out of a microprocessor relay like we got off of a electromechanical relay. And I said, you're correct, but we don't really know how long these are going to last. But if you get 10, 15 years out of them, we'll be happy. Well, that was the 1980s, and now it's the 2016, and some of these first-generation microprocessor relays are failing now. And they've been in service for 30 years, and now people are calling up and asking why these are failing. And I'm saying you got 15 more years of life out of those than I thought they would begin with. So they'll fail eventually, but they have a very good track record. At least they let you know what their health is and if they're imminently going to fail. Looking at the definition that we use for a relay is a device that responds to a measured quantity, current, voltage, heat, pressure, vibration, etc., from one system and switches a current in another system, usually an electric circuit, for the purpose of protection and control. Protective relays are devices that are used throughout the electric power system to detect abnormal or unsafe conditions and initiate some sort of corrective action. There are various different ways of classifying relays. One method is by function, and this is defined by IEEE C37.90, which is a Bible for the relay protection. The IEEE Power System Relaying Committee, more accurately, the IEEE Power and Energy Society Power System Relaying Committee is responsible for administering several of the standards, one of them being the C37.90, which is the Bible for relay protection. In there, we define functions such as protective device which detects the intolerable condition or some defective apparatus, a monitoring relay which verifies the condition in the protection and/or power system, a reclosing relay that establishes a closing sequence for a circuit breaker following a protective relay trip, a regulating relay that operates to maintain an operating parameter within a defined region, like a tap changer regulating relay, auxiliary relay that operates in response to another relay's actions so that it provides additional functionality. In the early days of microprocessor relays, when we had a limited number of contacts, we would use auxiliary relays to multiply those contacts so that we'd be able to trip several breakers or things at the same time. A synchronizing relay assures that proper conditions exist before we close a breaker in, so that the sections of the power system are about the same voltage and the angle between them is very small. So we don't put too much stress on the system when we close the breaker back in. You can also classify relays by input, whether it be current, voltage, power, frequency, temperature, pressure, flow, or vibration. All of these different inputs can be used to detect some abnormality or normality. You can also classify them by performance characteristics, whether it be an overcurrent, over or under voltage, a distance relay, a directional relay, inverse time, definite time, ground or phase, high speed or low speed, current differential, phase comparison, directional comparison. All of these are different performance characteristics that you can judge a relay by. Another one would be by operating principle, whether it be a current balance relay, we're comparing two different currents to see if they're the same or not, a percentage biased relay, as in a differential relay, a multi-restraint relay, a product relay, a thermal relay, a comparator, whether it be a phase comparator or a magnitude comparator. All these are different operating principles that relays operate by. And then again, we can also make a comparison by technology classification, whether it be electromechanical, solid state, or microprocessor-based. And a microprocessor-based relay could either be a digital relay or a numerical relay. However, we classify the relay can't operate on its own. A relay is a small device. It can't be hooked to a power system directly because it can't withstand the high voltage it would be applied on, nor can it withstand the high current that would be exposed to during a fault current conditions or even load current conditions. And of course, the relay has got such small contacts it can't open up a breaker, or it can't open a circuit if it should detect some kind of fault condition, because it's limited in how much current it can interrupt, for sure. So it has to be part of a system, and that system is composed of several components. One being the relay itself, of course, that detects the. So it has to have a source of taking these high currents and high voltages and reducing them down to some usable level that the relay could use, and those rely on sensors, whether it be a potential transformer, a current transformer, or a non-conventional current transformer for doing the sensing and then passing this information onto the relay. Then, as I said, the relay can't open a circuit up by itself, so we need to rely on a switch or a circuit breaker to do that for us. So the relay will tell the circuit breaker to operate. Then, of course, to make this all work, we have to have a DC-powered battery power supply to power up the breaker and the relay, if it's on an electromechanical relay, and possibly the non-conventional instrument transformer. Then we have to have this interconnect wiring between all the different devices to make it all work at all. Putting this all together, it looks kind of like this, where we have a current transformer, a potential transformer that's feeding into the relay that's doing the detection. Then once the relay sees this abnormality, it closes its contact, that you see here, it closes its contact, and then that contact then is in series with the battery that energizes the trip coil in the breaker, and the breaker trips and removes it isolates the area from the fault, and after the breaker operates, then the 52A contact opens up the trip circuit then. So if any one of these devices, if the PT or CT doesn't operate properly and doesn't give the information to the relay for the detection, the system won't work. If the relay itself doesn't respond to the CT or PT to make the proper decision, it won't work. If the battery doesn't work and doesn't supply the trip coil with current enough to trip the breaker, this won't work. If the trip coil is broken, if the 52A contact doesn't operate correctly, then we can burn up the contacts on the relay. If the breaker doesn't operate, it's a stuck breaker or something, then so any one of these devices, if it doesn't work properly, will cause the system not to operate properly. So let's go through some principles of relay application. We talk about selectivity, reliability, speed based on the need. You wouldn't necessarily have to have put an overcurrent relay on a transmission line because we want the relay to trip in a matter of cycles. At the same time, we wouldn't necessarily put a distance relay on a distribution line because we don't need to operate in a cycle or so. For that, we could use the time over current curve for that kind of operation. So speed is that we need to take that into account. How much speed do we need? Simplicity. The simpler the better is always the best approach on most of these things. And economics. What can we afford to apply where for backup protection and whatnot? Firstly, let's look at reliability. Reliability is a balance of dependability, which is the certainty that of a correct operation in response to system trouble, so that when trouble exists on the line, the relay detects and operates as it should. That's on the other side of the coin, there's security. And security means the ability to avoid an undesired operation with or without faults, which means that if the fault is outside my zone of operation, I don't detect it and I don't operate. So it's a dependability says I'm going to operate for any internal faults I see that are in my area. Security is I'm not going to operate for any external faults. So if you want to make something extra dependable, you may put two contacts in series with each other, and in parallel with each other, so that if main 1 or main 2 sees the fault, we'll be sure to operate and clear the fault. If you want something very, very secure, you can put two contacts in parallel, in series with each other, and so that they both have to see the fault before they operate. This way that if one misoperates, we won't cause a problem. So you can see that there's kind of an opposite ends of the spectrum, this dependability and security. So the relay designer and system designer has to balance one of these versus the other one. We can make a relay extremely dependable that operates for any fault in the system, but that won't do us any good because we need to only operate for certain faults within its zone of protection. Speaking of zones of protection, let's talk a little bit about our protection philosophy. We never let one relay stand by itself. We always have a relay overlap with respect to each other. And let's look at this from the standpoint of a system with generators, transformers, buses, transmission lines, and motors that we'll see in the next slide. Here we have 4 stations with some loads or another transmission line. We have a generator station with some transmission lines, some step-up transformers. We have a motor load at the bottom, some feeders. So let's look at that zones of protection here. Let's start with the generator. A generator has a certain generator protection is centered around the generator, and it should just protect for that generator itself. And so if the generator has a problem, we'll take the generator offline. The rest of the system is okay. So we just take that one generator offline. Oops. In the transformer protection, we will protect the transformer, but we'll also overlap that transformer protection with the overall protection, which encompasses from the neutral to the generator all the way up to the high side of the step-up transformer, including the high side breaker. So you can see that our transformer protection is actually overlapped our generator protection by quite a bit. And then now we put bus protection on top of that, and our bus protection overlaps our transformer protection by including that high side breaker in its protected zone. So as you can see that for every protection we have, we're always overlapping in the other zone of protection, so that no zone, we don't have any holes in our protection, and at least two things see most every one of the faults. Here we have a line protection that overlaps the bus protection. Then our motor and feeder protection will overlap the bus and line protection also. So you can see throughout our diagram here, we have all these different protections that are overlapping with respect to each other. Now this may not be a great overlap. And how do we get this overlap? Let's say on this generator step-up transformer, we have a high side breaker. And how do we just overlap around this breaker that you see here? And how it's done is we put our C current transformers on both sides of the breaker. This it's a dead tank breaker where we have available of the CTs on both sides of it, and we can see the CT for the green zone is taken, which is looking to the right, is taken from the CT on the left side of the breaker, and our red zone CT is located on the right side of the breaker, but it's looking to the left. As you can see, we're getting the overlap across these two CTs in this area. Just by way of knowing, the dead tank breakers, means that I can go up and touch the breaker frame or the breaker, outside the breaker, and it's at ground potential. That's what it looks like one of these. So these are all CTs here that you see on each of these bushings, and you can touch any part of this breaker that you see right here, and it's all at ground potential. A live tank breaker is different because it doesn't have CTs on both sides of it. Most likely we have to have a freestanding CT that's located on a pedestal either on one side of the breaker or the other side. When that's done, then our overlap is very small, and we have to know on these freestanding current transformers, it has one core, and then we have several CTs on the core. So we have to know where that CT is mounted on that core to get this overlap like we want. And that's what you're seeing right here, putting both these CTs on the same core on one side of a single live tank breaker. That's what a live tank breaker looks like as such. So there's no room for CTs because the CTs would be at a line potential way up there. We do, however, have these non-conventional instrument transformers that you can mount on a live tank breaker that could be used because they're not using iron core. They're using, and the information comes back down from the breaker instead of coming down on a copper wire. It's coming down on a fiber instead. Next week's presentation on input devices, we'll talk a bit about non-conventional instrument transformers and how they're used. Now let's look at some basic protection principles. Definite time over current, inverse time over current, directional, distance, differential, phase comparison, and directional comparison. All different basic principles of protection. Definite time over current is the easiest to understand. By definite time over current means that we have a set point for the relay, say over current element, so that say that the set point is set for 5 amps. That's what you see here. The pickup level, I pick up a set for 5 amps. And no matter what the current is over 5 amps, the relay responds at exactly the same time frame. So there's no delay in the pickup or the operation of the relay once it exceeds this just a 6 amp or 5 amp limit, whatever we set the relay for. And that's why you see its time is a straight line here. It doesn't change at all. And this could be instantaneous, or it could be a set time delay with a definite time, but it's a straight time. That's opposed to a inverse time over current relay that has this sort of a characteristic to it. Inverse time over current relay, we have a pickup level, as we said before, but as the current increases beyond the pickup level, the amount of time it takes for the relay to operate gets lower and lower and lower to some asymptotic value. So this is time over current versus instantaneous over current. What you see, it's an inverse curve relationship between the current and the time for it takes the relay to operate. If we have a circuit that has a radio line that has two breakers on it or two relays on this line to protect the circuit. Maybe this could be reclosers, this could be breakers, it could be whatever. And we have a fault on the far right-hand side that you see where that little squiggly line is on the right side of B. To coordinate these two relays together, we want the relay closest to the fault, between the fault and the source, to operate first, and then the relay further from the fault to operate second for coordination purposes. That means the relay at B, we want that to operate first, followed by the relay at A. So in order to do this, you can see this plot on the bottom. We want the relay at B to operate first, so we could first put B on this curve as we have plotted on this time current curve, as you can see right here. That B will operate first, and then we can use the same type of time over current curve shape in order to plot A with some time delay, so that A will operate after B. So you can see on here that A always operates after B. It's slightly changed in its orientation with respect to the time, so it's always operating slower. And this is how we coordinate relays together. And for a given current level, you can see that the distance between, this is a log curve. So the distance between the time between it takes the relay at B to operate and time the relay at A to operate is called a coordinating time interval between those two, and it should be the same for as the between the relays. So we have we'll let B operate first, and if B doesn't operate after a certain time, then A operates over this, and they coordinate together. And this coordinating time interval deals with the breaker operating time and whatnot, so we want to make sure that B has time to operate before A operates. Another sort of relay is called a over voltage or under voltage relay. This, we have a potential transformer that's hooked to a bus, and if there's two relays associated with this. One is called the 27 relay, which is an under voltage relay, and 59 relay, which is an over voltage relay. Two independent relays. So the 59 relay, if we set the relay at 120 volts and the voltage goes above 120 volts, then the 59 relay would operate. If we set the relay at 120 volts on the 27 relay and the voltage goes below 120 volts, then the 27 relay will operate. That's why we say we have a pickup value with this VPU here, and when the relay voltage goes above that, 59 operates, and goes below that, then the other one operates. Okay. The next relay is called a voltage balance relay. A voltage balance relay just compares the voltage on two different sides of an object together, and it's a comparison. And if they're the same, nothing happens. If one is higher or lower than the other one beyond a set point V difference, then some action is taken. These are often used for capacitor bank protection, where we're comparing two different voltages together, and if there's a voltage difference between the two, then we know that the capacitor has a fault in it, and we need to take some kind of action. In some cases, we can't just rely on overcurrent coordination, because you may. Oh, let's just go back to a couple slides here. Oops. In this particular case, we talked about inverse time coordination. We talked about this being a radial system, where that we only have current source at one end feeding radially down the line, so it was easy to coordinate between these two relays. If, however, we had sources at both ends of a line, so we had a loop system, so that we had current flow either from either or both directions, then it gets a little more difficult to coordinate these two relays together. And we'd have to know which way the current is flowing in order to determine how to work the coordination. In order to determine which direction the current is flowing, we go into a directional relay. A directional relay, we use not only do we use these operate quantity, which is this current, but we also have a reference quantity, and the reference quantity must be stable no matter which way the current's flowing. So we can relate the angle of the current between the reference quantity and the operate quantity to determine if the current's flowing in one direction or the other direction. In this case, we're using a current for the operate quantity and a voltage for a polarizing quantity. And you can see our reference is always going to be in the upward direction, and if current flows to the left, then it's going to be a non-operate quantity. And if the current flows to the right, it's going to be an operate quantity, and we call it a contact closing torque. And so we're able to determine direction by using another function, another element for doing the polarizing for us to give us this directionality. So when we do this directional relaying, we can use many different things for the polarizing quantity and the operating quantity. So for phase-to-phase faults, we typically use a current for the operate quantity, whether it be IA, IB, or IC, for each of different phases. And for the polarizing quantity, we oftentimes use a voltage that is 90 degrees away from the current, so that for IA we use a VBC for polarizing. For VB, so IB we use CA, and for IC we use AB voltage for polarizing. So we're using the non-faulted phases for polarizing. So we do that for phase faults and phase-to-phase faults. For ground faults, we oftentimes use 3I0 for the operate quantity and 3V0 for polarizing quantity. In some cases, we can use the polarizing quantity as an I0 coming from auto transformer or from another transformer at neutral instead, and just compare that to the 3I0 we develop at the fault. And now with the advent of microprocessor relays, it's much easier to calculate negative sequence quantities now. So oftentimes we can use a negative sequence current for polarization and negative sequence voltage for, negative sequence current for operating quantity and negative sequence current voltage for a polarizing quantity, as you see in the last case, 3I2 and 3V2. Okay. The next concept is called a distance relay. A distance relay uses the current and voltage at one terminal to determine the distance and impedance to the fault. The nice thing that we have about a power system is that the wires the wire has a certain number of ohms per mile or a certain impedance associated with it. So that by calculating what the impedance is at the relay to the fault, we can then estimate what the impedance is to the fault and calculate what the distance is to the fault. It's based on Kirchhoff voltage law, and we essentially wind up with three-phase loop, system loops: an A-B loop, a B-C loop, a C-A loop, an A to ground loop, a B to ground loop, and C to ground loop. And we calculate the current and impedances for each of these loops, and use a comparative principle to determine phase angle. A comparative principle to determine if the one impedance leads another impedance to determine whether or not the fault is internal or external. Here we see this phase comparison that's being used for in this particular case for the distance relay. What this does is it compares the phase angle of the two voltages derived from the system voltage and the currents during the fault, which means S1, which is one of the inputs of the comparator, is IR times ZR minus VR. This is what that one quantity is equal to. And then S2 could simply be VR. Now, S1 IR minus IR ZR is actually the voltage drop from the relay to the fault across this line. Then VR would be the voltage at this point at the source here. So that comparing, then you could recompare that to the VR by itself and determine if the S1 leads S2, then the relay will operate, and if it doesn't, it restrains. So we have a constant operating torque when again, this is looking at this rotational counterclockwise rotation. So if S1 leads S2, that it operates. If S2 lags it, S1 lags S2, then it restrains. If we do that, we construct a Mohs circle, which is this circle that anything that within this circle is the operate. Well, the relay will operate, and the outside the circle, the relay will not operate. So if we draw this on the Mohs circle, if we draw this line, we have a source ZG down here to the G bus. Then we have the line impedance to ZR, and then we don't ever protect for 100% of line, so we have this. So it's set for like 80% of line or so. Then we have this rest line impedance. Then ZH would be the impedance of the Thevenin impedance of the rest of the system beyond that bar bus. This is called a self-polarized Mohs characteristic. Another type of protection we have is called differential protection. Differential protection involves Kirchhoff's law again, and it's very simply looking at the current going into an object and the current going out of the object and making a comparison. Kind of similar to what we did in a voltage differential where we compared the two voltages. Here we're comparing two currents. And under normal non-fault conditions or external fault conditions, the current going in is equal to the current going out, and there's no operate current at all. But under fault conditions, the current going in does not equal the current going out, or the current going from the other sources turns and forces the other direction, so that we get a operate current, and we can trip for this operate current. So during an external fault, we get no operate current, and for an internal fault, we get lots of operate current. Now, there's other complications with using current only, is that you could have CT saturation and all that could influence whether or not we get operate current or how much operate current we get. But modern relays have ways of detecting and operating for this this kind of currents nowadays. So this differential protection is for generators, motors, transformers, transmission lines, buses, shunt reactors. Any of these we could use equally as well. Another type of couple types of measurements for a bus differential relay will measure all the currents on each of the different inputs coming into the bus and add them together to see if they add up to zero, and if they don't, then we'll get a operate current flowing through an operate coil and operate the relay. Another type of protection, differential protection, is called a partial differential, where we look at the currents flowing through each of the phases, and we add them together. And of course, the summation of these three together is equal to 3I0. We compare that current to the current flowing in the neutral, and under non-fault conditions, that these will balance out with respect to each other. But when we get a ground fault, then they won't be equal to, and will trip right away. This could be called restricted earth fault or partial differential, both on the same kind of name. Another two types of protections we can use. One's called a low impedance bus differential scheme, where we just add up all the currents together coming into the operate winding, and the operate current, differential current, is the sum of all the currents flowing through each of the different feeders or sources. And another kind is a high impedance differential relay, which we put a high impedance across we parallel all the CTs together, put a high impedance across them, and then when there's a differential current between them, we develop a high voltage across this high impedance, and then we monitor that with a voltmeter and or voltage element, and then when the voltage gets high enough, we'll trip the breaker via this over voltage element. That's called a high impedance differential. And high impedance differential has been around for years and years, starting off with the PVD, then the KAB electromechanical relays, and now it's gone over into the microprocessor type relays nowadays. It's very, very fast. You can put as many CTs as you want in parallel. The only thing is you have to match the CTs together to have the same kind of knee point voltage and stuff on them, and some other criteria. But it's been used for many years. When we use the basic differential protection, we need to account for, because we're so much looking at current alone out of each of the CTs, we need to have the CTs to perform nearly exactly the same. Otherwise, we wind up getting a false differential current if the CTs aren't performing exactly the same. To account for this false differential current we get from CTs not operating quite the same, we wind up using a multi-sloped differential characteristics, so that under which is shown on the left right here, under very, very low current conditions between 0 and 1.5 per unit or so, then we have a kind of a flat line, so that we don't bias the currents at all. So that this is a graph of the operate current, differential current versus the restraint current, and what you see on here, this multi-slope line, is the operate reach point, so that anything above this slope line is the operate area, anything below this is restraint region. So that under the low current conditions, there's no intentional bias on this, and we get a flat operating area region. As we start getting higher and higher in restraint currents, we're going to start seeing a mismatch of the operation between the various CTs, possibly, and there's going to be some error current, and to accommodate for that error current, we had this slope on the line. So so for these slopes, it's going to take us more differential current to operate than we had under the lower current conditions. And then as we get past a certain point in this particular graph, it's 4 per unit, then it takes, we're sure that one of the CTs is going to saturate. So we're going to bias for that. We have a very, very large slope so that we can accommodate for that saturation from that CT. And the slopes for this typically, this M2 slope is typically 40 to 60%, and this M3 slope is typically 80% or so, up to 100% for this M3 slope. So you can tell there's much more current to operate in under those high current conditions than the lower current conditions. Another way of is to give it some directional capabilities. We know that for we're looking at the angle between the two currents. We know that for an internal fault, that the reference current and the operate current are going to line up pretty much in the same boundary. So they're going to be in this operate area that you see on the right-hand side here. But when there's a external fault, then ideally the operate current and the reference current are going to be in opposite directions, so that it will be in this external fault area here. So we can actually put a security angle built into the relay so that we know, so that the operate current and the reference current are within this relationship with respect to each other, then we'll operate, and if it's beyond that relationship, we won't operate. So this is another way of binding the operation of the differential element so that it operates properly for internal and external faults. We could do this. This is what's used quite often on a negative sequence differential element. Now, taking that same principle that we had for the differential relay, where we're only using one relay, but CTs coming into the relay from both sides of the protected object. Now we expand this to a line differential relay, and the line differential relay actually is using current as we did before in the differential relay, but all these currents are separated by miles and miles, so that now we have two relays located, one local and one remote. We have a pilot channel between them, which is a communications channel, and we send the current information from one end of the line to the other end of the line, both directions, so that each end of the line compares the local current and remote current and determines if it's an internal or external fault, such that, and this is what happens with a line current differential relay. It just compares the local and remote current over this pilot channel. For this to work properly, and it's the easiest relay to use and to apply, but the only caveat to a line current differential relay is that the pilot channel has to be very, very secure. And we have to have, if we don't have current flowing, if we don't have the pilot channel working, then we don't know what's going on at the remote end of the line, and we can't make a trip decision or not. So we need that for sure. So you do things like putting dual pilot channels in or something, so we're sure we get the information from the remote end to the local end. But if that's established, then it's very, very simple relay. And there's virtually no settings involved. You just compare the local to the remote. And if they're in phase with, or if there's a differential current, then we operate. If there's non-differential current, then we don't operate. So using the same pilot channel approach, we can take an impedance relay. And remember before when we first talked about the impedance relay way back when, back over here, we said that in the impedance relay, we can only reach for 80% of the line, and for that last 20% or whatever your utility philosophy is, that last 20% of the line, we can't trip high speed. Anything between the origin and the relay reach, we're going to trip instantaneously within a cycle or so for that kind of a fault. But for that last 20% of the line, we have to we can trip the remote breaker and for the feed from in that direction, but for this 20% line from the sources ZG, we have to rely on zone 2 tripping, which means we're going to trip with a time delay upwards of 30 cycles or so. Well, if you want to trip this instantaneously, that last 20% of the line, then we have to do the similar thing that we did with the differential relay, and that is have a pilot channel, so that the G end of the line and the H end of the line have to share information. Like the G end will say, I see a fault in the forward direction, and the H end will say, I see a fault in the forward direction also, but he's just looking toward the G end. And if they both say that they see a fault in the forward direction, then they'll trip both ends instantaneously. So that's kind of what the pilot systems do for the called directional comparison. So that's what we're showing here. In this case, we're showing that in a POTT scheme, the permissive overreaching transfer trip, the one end of the line that will send a permission to the other end of the line, but the other end doesn't, so that they don't trip at all. Because here we have an example of an external fault right here. For an internal fault, which is in the line, then this end sends a POTT saying, I see a fault in the forward direction, and this one does the same thing. So they both exchange that information, so they both trip. Same thing with the permissive underreaching transfer trip. So these are the permissive overreaching transfer trip, the permissive underreaching transfer trip, the unblocking scheme, and the blocking scheme are all ways of tripping the entire line without waiting for that time delay for the last 80%. The blocking scheme is a little bit different, is that the blocking scheme is only looking behind the relay instead of forward looking. So that, let's say the fault is in this particular case, here. Like here, the fault is behind this relay at this right end of the line. So this relay at this end sends a block to the remote end of the line saying don't trip. So this then receives a block signal, and this end sends a block signal. Whereas the fault is in the forward direction, then they both see the fault in the forward direction, and they don't receive a signal that says don't trip, so they both trip. So it's a little bit more dependable than because it really doesn't rely on the pilot channel to trip, but it relies on the pilot channel to prevent tripping, so it's not quite as secure as but it's used quite often. Next thing is IEEE device numbers. As I said before, we have a way to represent what overcurrent relays, undercurrent relays, overvoltage, undervoltage. So we have to have some way of representing all those devices. So we do that by using device numbers, and device numbers are listed in IEEE standard C37.2, and this is always being updated every 5 or 10 years or so. And it gives you the definitions of all the devices and their numbers and what they are. So it's such as in the last go around when the microprocessor relays were starting to become more predominant, they needed a device number to describe what the microprocessor really was, this black box. So they came up with the device that you could see. This is device number 11. And device number 11 could contain many other devices within it, because it's a multifunction device. So device 11 was a multifunction device, and you can have things like the 50 element, which is time instantaneous overcurrent, 21 elements, which is Z1, Z2, and 3 zones of overcurrent, impedance elements on there, ground distance elements in it, and whatnot. So that device 11 was the overall device for a microprocessor multifunction relay. And how you label each of the individual components within it, you can either do it by filling the box method that you see right here, or do it by listing them. that you see on this page, where we have this 11th element, and then in the 11th element we have all these devices within it. And then lastly, we have again, I'll refer you to C37.2 for all the different types of device numbers that are being used within industry now. And then on this C30, we also have device graphic symbols for the IEEE and for IEC. And I'm just saying this because oftentimes wherever you get your drawings from, they may have one or the other type of nomenclature on them. Let's go through a little bit of this. A normally open contact, then the IEEE is just two parallel bars with the open on it. And the closed contact is just two parallel bars again with a line going through the two of them. So Form C contact would have one normally open and one normally closed, which you see right here. But in the IEC world, the normally closed contact is just showing you like a flapper that's open, and then a flapper that's closed for the normally closed contact. And then the Form C is one open and one closed. In the circuit breaker, we just represent in IEEE world as a rectangular box. In the IEC world, a fault is a breaker is represented by a X. So I just want to make it clear that in the IEC world, the X means a breaker. In our world, in the IEEE world, the X means a fault on the diagram. So we have to be clear about those two things. Then our disconnect switch is similar to what their normally open contact is, and the motor operated disconnect switch has a motor operator on it. 2-winding and 3-winding transformers we use the winding representations with delta Y on them, and in the IEC world they just use two intersecting circles for the 2-winding transformer and 3 intersecting circles for the 3-winding transformer. And the auto transformer is one shows one winding with a tap on it, and there it says it looks like a bicycle, like a circle with a tap on it, 2 taps on it. And in current transformers, we have we use a winding again with the polarity marks on it. In the IEC world, they just show a circle with a line coming from it. And our normal phase designation is either ABC or 1, 2, 3, and in IEC world it's RST. Then we use the same designations for the positive, negative, zero sequence components. In current is the same as I, but in voltage we use V, and they use IEC uses U. So that's our seminar for today. That's a little bit over an hour long. It's brought to you by the Railline series and RTU 500 and Microscada and Tropos. And if you want more information on this, you can go to the relays. You can go to www.abb.com/Railline, and all of our YouTube channel has many pieces of information about products and demonstrations and whatnot, and that's www.youtube.com/ABB SAP Products North America. Okay, I didn't tell you before the presentation, and I should have said that the webinar itself is on the, if you look at the right-hand side in that bar again, and you can see that Introduction to Protection and Control webinar is on here, and you can click on it and download that for yourself. Carrie will send you a link to get this also when she gets back from vacation next week. Now now that we've gone through this, I'll go back and I'll see if I can get these, if anybody asks any questions or not. I'll go to here and go up to the top and see. I don't have any background music on, so I'm not sure why you should have any background music on here. I'm sorry if show any background music at all. This presentation is being recorded, and the recording will be available for you to look at. The next question is, what is the difference between a numerical relay and a digital relay under microprocessor relays? A numerical relay takes the information from the out of the A to D converter and uses just ones and zeros to go through the processor, and everything is done with that. Where the digital relay is just, it's like our first generation of microprocessor relays, where we didn't use all of the how do I want to say this? We didn't use all the values weren't just using ones and zeros, so we're using some of the analog values into the relay also. I guess I'd call it that way. So it just wasn't all numerical. Some of it was also using analog information also into the relay. What is an NCIT sensor? NCIT sensor is a non-conventional instrument transformer, and that could be either using a Paco cell for a voltage sensor. It could be using a fiber optic CT for a current sensor. It could be a Rogowski coil. Anything that doesn't use the conventional electromagnetic circuit for the current and voltage is a non-conventional instrument transformer. And now those devices can actually be streamed with the IEC 62850 information into the relay without having to go through any kind of A to D converter anymore. I have a pop-up window blocking the presentation. Uh-oh. I wonder what that was. I'm sorry if it was the case. Oh, now it says no pop-up window blocking the presentation now. Okay. Oh, shoot. I had a lot of Apple push messages. I cleared that later on, so I hope you weren't seeing it the whole show. Let's see, eventually this has to be done. Finally, I'm sorry that for part of the presentation there was a pop-up window that was up there, and I finally looked over and saw that. I was looking at one screen, you guys were looking at another screen, so that's why it didn't appear right away. Otherwise, probably if Carrie was here, she would have told me that, but I don't hear anybody's voice or anything. Of course, they're all blocked, so I didn't hear that. But hopefully, it got cleared eventually, so after a half hour, it was up and cleared, and you could see it okay. Now it says, what is the significance of using a factor of 3 for zero sequence polarizing or operating quantities? Is there any special advantage of using 3I0 versus I0? Well, it's just when you derive the currents, adding the three-phase currents together, you automatically get 3I0. So it's just easier to use that quantity. And because you're using a 3I0 rather than I0, you have a little bit more of a quantity to use the expression, so that the sensitivity is greater than if you use the I0 value. So that's why 3I0 is quite often used. Easier to generate and more sensitive. than using just I0. Can you give an example of a pilot channel? Yes, a pilot channel would be like a fiber optic channel, could be power line carrier, it could be a telephone, it could be microwave, it could be leased line, it could be I guess in some cases spread spectrum radio. Any method of communicating between two stations could be used. Quite often nowadays, you even embed fiber optic into the transmission line in order to generate, in order to do the communications between two ends of a line. So on any of those would be pilot channels. In simple overcurrent scheme, it shows all feeders being added to ID. Is there a set value at which the ID limit is met? How is the relay know when to trip? Yes, the ID is the differential element, and usually the ID minimum is a setting within the relay. Usually the ID minimum is set for like 0.5 per unit, where 1 per unit would be like whatever their CT size would be. Like say you had a 1205 CT, then the 0.5 would be set for 600, would be like 600 amps. So that's typically what the ID level is set for. What is a good reference for protection settings? For instance, for a motor power rating, what is the maximum current? Same for transformers. Well, motor rating would be given by that however many horsepower it would have, and you could convert the horsepower to watts, and then you convert that watts to whatever the voltage would be, and determine what the current is in order to determine what the rating would be for the setting for the relay for the motor. So typically you set the motor in terms of full load current and locked rotor current, and you kind of draw a line between them for the operating point for the number of current curve. For a transformer, I'm not sure what setting you're talking about here. For a transformer, you'd usually put a differential relay to protect the transformer, and that differential relay would have a minimum setting on that, and that minimum setting for the differential current on a transformer is usually composed of several elements. One being what the if there's a tapped changer on the transformer, if there's a so that you have to set the ID minimum above what the normal expected differential current is going to be, and that it's affected by the winding, the tap changer, the CT capability, and the no load current in the transformer and whatnot. All that exciting current in the transformer. So all that it determines what is going to go into being the minimum setting for the differential current on the transformer. We're having another presentation in a couple of weeks on transformer protection, and we'll go into that much more detail then. How do you think relay will have to change with the more emphasis on microgrids, possibly and more options for bidirectional relays? Yes, as we get more and more microgrids, we're going to and actually putting more and more wind turbines and solar arrays on power systems. We're going to be having more and more dispersed generation. So we're going to have more and more directional relaying, and plus these microgrids, wind turbines, and that are solid-state supplies are very different than what we're used to seeing from machines with big masses that give us lots of fault current. For instance, on a inverter type scheme, the amount of current that a device will put out for a fault is limited to 1.5 times the normal full load current quite often, and it's also limited the duration it will put it out for, just a short burst of time before it shuts itself down. Compare that to a infinite bus or a synchronous generator, which will put out a bunch of current, like upwards of a 10 per unit current for a period of time, much longer than these electronic inverter systems will put out. So everything is changing with respect to protection for those, and it's much harder to protect them, and we have to be much more cognizant of what is on the system for generation sources rather than what we used to believe before. You closed the window partway through the presentation. Uh-oh. When and where are life tank breakers typically used? Typically, a life tank breaker is used on very high voltages where they're cheaper to build. There's less insulation that you have to put on them, and they're used at 345 kV and at 500 kV or so. Oftentimes, a lot more are used in Europe than used in the States, and a lot more used in Japan than we're seeing in this country. But yeah, so that's kind of where they're used. Where they get to be, as the voltage level on the breaker goes up, it gets to be more and more expensive to make it into a dead tank breaker. Between the POTT and DCB line current differential, can you briefly explain the difference between the POTT, a DCB, and line current differential? Sure. In a POTT scheme, we're using typically a impedance relay or distance relay at both ends of a line, looking, and each one of those impedance relay is set for like 150% of the line, so that it's looking way past the far bus of the line. So we have one relay looking down one line in one direction, and we have the other relay at the row terminal looking in the other direction, each set for typically 150% of that line, so it's way beyond the far bus. So when the fault is internal, both relays overreaching elements will see the fault, and they'll each tell each other to trip. So you'll get permissive from the other end to trip. So that's how that works. When there's an external fault, the one relay at one end of the line sees a fault in the forward direction, but the relay at the other end doesn't see that fault because the fault's behind it. So it doesn't send permission to trip, so the relay doesn't trip at all for that case. So that's how the permissive overreaching transfer trip system works. A directional comparison blocking scheme works opposite of that. A directional comparison blocking scheme, at each of the terminals, we have a relay that's looking backward toward and the relay looking forward. If the relay looking backward sees a fault behind it, it sends a blocking signal to the remote end saying, I know you may see a fault, but don't trip because the fault is behind me. So it blocks the relay from tripping. If the fault is in the forward direction, both relays see it in the forward direction, and no relay sends a blocking signal to the remote end, so they both trip. So that's kind of how a directional comparison blocking scheme works. And for a current differential scheme, it doesn't use impedance relays; it just uses current, and it has a local CT that develops a current and feeds it into the relay, and then the communication channel will send the remote information from the CT from the remote end of the line to the local relay. And the local relay does a differential comparison. It calculates what the ID current is, the difference between the local current and the remote current, and calculates that operate current and calculates the differential current and uses the same kind of a curve we showed you before, that restraint current that says if my operate current is so much, and then my relay will operate. So that's how the line current differential relay operates to clear that kind of a fault. Again, all the line communication channels. Do microprocessor-based relays need air conditioning? Well, they all have limits on the amount of. The microprocessor relays have limits on how hot they can get. And I live in a cool climate, so I don't have to. You don't come up with that very often, but they have to stay below. And the temperature is given in the ANSI standard C3790, but it evades me right now. But they have to stay below, I want to say 40 degrees C or so. Otherwise, they get too hot, and so they'll have to air condition the relay. But it's not like a computer, but the relay will keep working. But oftentimes, if it gets too hot, the LCD display will go black or something. But the relay will keep working. But so you get above a certain temperature, and yes, they're going to have to be air conditioned. My question is much more reliable. Which is more reliable, electromechanical, solid state, or microprocessor-based relays? Well, that question is a good one. We know that if you maintain an electromechanical relay, which means you do maintenance on it every year, and burnish contacts on it and give it a check and whatnot, then it will last for upwards of 50 years. We also know that, but it doesn't do any self-checking at all, so if something does go wrong with it, you won't know it. In the microprocessor-based relay, because it has lots of self-checks built into it, you don't have to do as much maintenance on it, and it will look at its CT circuits to make sure they're okay. It'll look at the PT circuits to make sure it's okay. It will look at the data converter, make sure it's working all right. And so it does a lot of self-checking within the relay, so it is self-monitoring. So if something does go wrong with it, it will tell you if something was wrong. To say which one is more reliable is a hard question. If it was a standalone substation with nobody touched it, then I would say the microprocessor relay would be more reliable. But if you do maintain the maintenance on the electromechanical relay, then it will be a very reliable relay also. So I guess it's kind of hard to answer that question. What do we use as IRES and IDIF for the differential relay? Would you recommend using 2 microprocessor-based relays per relay terminal to provide redundancy? What do we use for IRES and IDIF for a differential relay? The IDIF and every differential relay, the IDIF is the same. It's the absolute value of the absolute value of the sum of the 2 vector inputs to the relay. And if it's a 3-winding relay, or if it's a 3 restraint relay, it's the algebraic sum of the absolute value of the sum of the 3 inputs to the relay. So that's what the operating quantity is, and that's pretty much constant. The restraint quantity is different from manufacturer to manufacturer. It could be the average value of all the restraints added together. It could be some multiplier times one of the restraints. In some relays, it's the maximum restraint in any one of the phases. So, like if you had a 3 restraint relay with 3 CTs, then you look at all 9 CTs and see whichever one of those restraints is the greatest. Then that would be the restraint quantity that's used. So it depends from manufacturer to manufacturer what is used for I restraint. Would you recommend using 2 microprocessor-based relays per relay terminal to provide redundancy? Well, if these are high voltage lines over 100 kV or so, then you need to have a main 1, main 2, and oftentimes people will use two microprocessor-based relays, two line differential relays for primary and for backup. But it's important also that you have two redundant channels there too. Because as important as the relay is, if the channel fails, then the relay won't work either. So it's important to have redundant channels there for if you have two relays, just so that we have a good channel for the communications at all times. CCPTs are as accurate as regular PTs. Oh, CCVTs, you mean? Yes. And again, a CCVT is a coupled capacitor voltage transformer. And it's used, again, when you get above 138 kV, and that's probably the breakpoint, 69 kV, then it gets to be too expensive for most wire-wound potential transformers, and people switch to a capacitor CCVTs instead. And they're as accurate as a PT is, because we can do things within the circuitry in order to make them accurate. There are certain things that, because the CCVT has capacitors and inductors within it, it will have some ring down effects, and it will have some residual, what you call the residual. What is that word? Residual voltage on it. When you remove the voltage on, or when you apply a voltage to when the line's closed, the CCVT doesn't respond exactly right. It overshoots that voltage is supposed to be, so you get some overshoot. So the voltage goes high for a little bit, or when you take the voltage off, it doesn't go right to zero right away because you get this ring down. And depending on how much capacitance is in the CCVT for the total capacitance, depending on what the tap voltage is, depending on how the design of the Herb resonance suppression circuit is, all of these things affect the transient response of the CCVT. In order to, but typically, if you use a CCVT with a second or third generation microprocessor relay, they take into account this response that the CCVT is going to have, and it account for it in the relay logic. So that's a good thing, at least. So they are as accurate as a PT in the long term, but just for the short transient response, it may not be quite the same. What are the guidelines for selecting a 51 over currents? What are the guidelines? Oh, 51 curve. Okay. Well, I guess typically those curves were developed back in the electromechanical relay days, because it was the interaction between the induction discs that these old relays were first made up, electromechanical relays were first made up, and the electromagnet that was the E magnet that was around this disc to make it spin would cause these different curve shapes. So when they went to developing from electromechanical relays to the microprocessor relays, they kept the very same curve shapes, but generated them by numerical logic rather than using these electromechanical physical phenomena to develop the curve shapes. Which one you use depends on what the application is going to be for. If you look at the distribution circuit, which are more or less used on, if you want to coordinate this with a fuse, and a fuse has a certain curve shape, then you have to use the same shaped curve on the overcurrent element, the, which means a fuse shape, and the type of time over current curve that you use have to be kind of matched in order so you can do the protection coordination between the two of them together. So that's kind of, and I guess that's about how you can do it. Like if you look at the what's installed right now, because most of these aren't really are installed on our replacement relays or whatever you have installed right now, you have to coordinate with what's out there. Typically, the curve shape is taken so that it will coordinate with what's in the circuit already. Like if you have a bunch of CO11 instantaneous, if you have a bunch of very inverse time overcurrent relays installed, then you're going to use a very inverse overcurrent curve in order to coordinate with those other ones, because otherwise the shape would be wrong. And that's kind of, so it's not really an easy answer which one you use. It depends what the conditions are and what you're coordinating with as to which ones you'd actually wind up using. I guess that's all the questions that people have had, so I think I'm about ready to close out the seminar. Thank you all for tuning in. We had, I'm sorry there's some mechanical problems before until I noticed that and closed out that that problem with that coming up on the screen before. But now that I finally resolved that, it worked out all right. So, but this whole webinar will be on. You can get a copy of all the slides by clicking on that. Click on the bottom under where handouts are. You can download that protection and control so you can see all the slides without having that thing in anymore. And the whole recording will be online for you to see also. So thank you all for tuning in. Next week, I said there'll be input devices going on, and you can all listen to that also. So goodbye. Have a good day, and hopefully we'll talk to you again sometime. Again, this is Roger Hedding with ABB signing off.